Hello there, my name is Kaylin Waters. I am working with Group 8 and we will be covering Chapter 6, Section 5 of the textbook, which is molecular geometry. We will be covering intermolecular forces, the VSEPR theory, and hybridization. Let's begin. Intermolecular forces are forces of attraction between molecules, which vary in strength but are usually weaker than bonds. Intermolecular forces happen when molecules influence the physical properties of something. For example, H2O is water in all of its forms, but its physical properties are different. Dipple forces have strengths that vary from 5 kilojoules to 20 kilojoules per mole. They have a significant effect when moles are near to, touching, or are touching, and are much weaker than ionic or covalent bonds. 4 molecules have partial, negative, and positive ends. The ends attract to the opposite charge of another molecule. Hydrogen bonds are weaker than ionic and covalent bonds and are attached to one of the most electronegative elements, which causes hydrogen to have a lot of positive charge. Hydrogen bonds can be created by atoms in different molecules or in parts of the same molecule. The London dispersion force is the weakest intermolecular force. London dispersion forces are a result of constant motion in electrons that create instant dipoles. London forces act between all atoms and molecules, but are only intermolecular forces acting among noble gas atoms and nonpolar molecules. Let's move on to the VSEPR theory. The VSEPR theory, or pronounced VSEPR, like the creepy little thing that's in the bottom corner, is a model used to guess the shape of single molecules using the electron pairs that the atoms have. This model takes its elements mainly from the Lewis dot structure and the electron regions represented. For example, 3 atoms in a bond will come to 2 electron regions, 4 atoms produces 3 regions, and so on. A model can exist in 2D form for up to 3 regions, but once we get to 4, scientists have to use a 3D model. All of these diagrams have names. A 2D model, for 2 regions, it is a linear diagram because the regions form a 180-degree angle. 3 regions are called trigonal planar diagrams and take the form of a pie chart in 120 degrees. 4 are tetrahedral diagrams sitting at 109.5 degrees, known as expanded octets. 5 are trigonal bipyramid diagrams, and 6 are octahedral diagrams. With octahedral diagrams, bonds form at 90 and 180 degrees. For example, here we have a methane molecule. On the left, you'll see the Lewis dot. On the right, you'll see the Lewis dot structure, and on your left, you'll see the VSEPR model, which would be a tetrahedral diagram. Sorry for the pause. Now, you may be asking, what about the molecules who don't have pairs for all of their electrons? The electrons do take up space in a molecule, but they mangle the shape of it, creating an uneven space in between. And for your example, you will see an ammonia Lewis dot structure diagram. Now we move on to hybridization. Hybridization is the mixing of 2 or more atomic orbitals of similar energies on the same atom to produce new hybrid atomic orbitals of equal energies. Methane is a good example of how hybridization is used to explain the geometry of molecular orbitals. The orbital notation for a carbon atom has 4 valence electrons, 2 in the s orbital and 2 in the 2p orbital. How does carbon form 4 equivalent tetrahedrally arranged covalent bonds by orbital overlap with 4 atoms? 2 of carbon's valence electrons occupy the 2s orbital, and 2 occupy the p orbitals. The 2s orbital and the 2p orbitals have different shapes. To achieve 4 equivalent bonds, carbon's Two s and three 2p orbitals hybridize to form four new identical orbitals called sp3 orbitals. What are hybrid orbitals? Hybrid orbitals are orbitals with equal energy produced by the combination of two or more orbitals in the same atom. The number of hybrid orbitals produced equals the number of orbitals that have combined a molecule of methane by bonding with the carbon sp3 orbitals.